Hey everyone, this is week 0 of my journey through convex optimization and machine learning theory. I'm a recent graduate currently working as a data scientist, and I'm starting this channel to document what I'm already doing, which is teaching myself convex optimization and studying ML theory more rigorously. With that in mind, let me tell you what led to learning convex optimization and ML theory. So, I recently took a linear programming class. And going in, I was sort of expecting it to be mostly algorithms, but I was wrong. I mean, it was some algorithms, but it was also lots of theory, and I thought the theory was really elegant. I mean, you had the geometric interpretations, you had dual theory, how everything sort of connected together, like in flow trees. It really opened my eyes to a rich field. What's more is I realized that optimization is really the language of machine learning. Nearly everything in machine learning reduces to defining a loss function and then optimizing it. So without understanding optimization theory, you don't really know when your algorithm will converge, what theoretical guarantees you have, or what the geometry of your problem looks like. I remember in my optimization class, we were tasked with writing support vector machines formulated as a linear program. So if I want to understand ML deeply, not just apply it, but really understand it, I need to understand optimization rigorously. Okay, some background about me. At university, I took 2 machine learning classes, supervised and unsupervised learning. I enjoyed them, but always felt like I wanted to learn more about the math behind it all. I mean, we did do lots of math in those classes, that's true, especially unsupervised, but I know now that there's a lot more math. Then I took a linear programming class using the Vanderbei's textbook. We covered the simplex method, dual theory, network flows, and integer programming. I did very well in the class, but more importantly, I got genuinely interested. After the class ended and just recently, I worked through the rest of the textbook, including dual simplex, game theory, and other applications like assignment problem or shortest path problem. So you might be wondering, if I already took a class in linear programming, why not just stop there? Well, the reason is that a lot of machine learning problems aren't linear, and a lot of the theory in convex optimizations are actually generalizations of those from linear programming, which is what I enjoyed in that class. For example, logistic regression is convex but nonlinear. Support vector machines with kernels produce nonlinear decision boundaries, though the optimization itself is still convex. So I know that understanding optimization will set the foundation to really understanding ML. I'd like to show you some of the elegance of linear programming. Consider a simple production problem. A factory produces 2 products. Let's call them product A and product B. Product A gives $40 profit and requires 2 hours of labor and 1 material. Product B gives $30 profit and requires 1 hour labor and 1 unit of material. You have 100 hours of labor available and 80 units of material. How much of each product should you make to maximize profit? So let's write out the optimization problem. So how we do that is we let x1 be the units we produce of A and x2 be the units we produce of B. And we want to maximize, of course, the profit, which is just the sum of the number multiplied by the profit of each. And of course, we can't make this to infinity because we only have 100 labor hours and 80 materials. And here's our constraints. Notice that both the objective function and all constraints are linear functions of the variables, meaning that there's no x squared or anything like that. So how do we solve this type of problem? Well, the insight comes when we graph it. So in the blue line, you see the labor constraint. So this line is a line such that 2x1 plus x2 is equal to 100. And since it's less than equal to, whatever our solution is, it must be left of this line. Likewise, the red line is a material constraint. We can't produce more than 80 units because we only have 80 materials. And so whatever the solution is, it must also be left of this line as well. Notice we also have a vector pointing in the direction of increasing profit. And we want to find a point in this feasible region which maximizes that profit. And you can see that it turns out the solution is here. Notice that the feasible region, which is the region which is light blue, which is the region where we could have possible solutions which satisfy these constraints. Notice that it always produces what we call a polyhedron, these sort of intersections of half planes. We want to find the point in the feasible region which maximizes profit. Now, just looking at this picture, you can kind of see, yeah, this solution makes sense. If we want to go as much as we can in this direction, then this must be an optimal solution. But what happens when you have more than 2 or even 3 variables, and you have to plot this feasible region in higher dimensional space? Or what happens when you have many constraints, and it's harder to just see what the optimal solution is? So that's why we need the simplex method, which is a way to arrive at the optimal solution. So geometrically, how the simplex method works is that we start at 0. In this case, we have profit of 0 at 0, 0. And then what it does is it jumps from vertex to vertex of the polyhedron that's defining our feasible region. So in this case, it jumped from the 0, 0 point to this vertex, which crosses the labor constraint. And then it goes from the labor constraint up all the way until it hits the material constraint. And then it looked for other vertex it looked for, but it turns out that these points here won't increase the objective function any further, and it stops. So this is the geometrically what's happening with the simplex method. And I think that's pretty cool. Now, every linear program has this general form. We call it the primal problem. So we try to maximize the dot product between C, our cost vector, and X. And we have subject to constraints here. And you can see, for this example, what the values were for these matrices. Now, where it gets really interesting is that every primal problem, so this one here, has an associated dual problem. It's constructed mechanically from the primal, but it reveals completely different economic interpretation. For the dual, we introduce these new variables y, and we write minimize b transpose y is subject to a transpose y is greater than or equal to c. So notice how everything is kind of flipped. The c in the objective function goes down into the constraints, and the b from these constraints goes up to the objective function. And we can see that A is transposed here, and the inequality is also flipped. So back to our production problem, the dual asks, what should the shadow prices be for labor and material? So concretely, let Y1 be the value per hour of labor, and Y2 be the value per unit of material. So think of it this way. Imagine somebody offers you to buy your resources instead of using them for production. What should they pay per hour of labor and per unit of material? Those Y values are those prices. So looking at our first constraint, What this says is that the total value of resources needed for product A, 2 hours of labor at price Y1 and 1 unit of material at price Y2, must be at least $40 because that's the profit that product A generates. So if it were less than 40, you wouldn't want to sell those resources and you'd want to make product A instead. Same logic for product B. So the dual is asking what's the minimum total value you can assign to your resources 100y1 plus 80y2 while making sure that the resource value needed for each product is at least as much as that product's profit. Another way of thinking about it is these shadow prices tell you the marginal value of each resource. If you can get 1 more hour of your labor, your ultimate profit would increase by $1. That's why they're called shadow prices. They reveal the hidden value of each constraint. Now here's the really cool part, I think. This is all great and all, but there's 2 fundamental theorems. First, we have the weak duality theorem, which just says that the dual objective, so B transpose Y, that's what we're trying to minimize, is always an upper bound on the primal objective. So if you have any feasible solution to the primal and any feasible solution to the dual, the primal's value is always less than or equal to the dual's value. I mean, this makes intuitive sense. Any valid resource pricing gives you an upper bound of the maximum profit you can achieve. Finally, for a strong duality theorem, if both problems have an optimal solution, then they have the same optimal value. The maximum profit of the primal equals the minimum resource value of the dual. This means that the maximum profit you can make from production equals exactly the minimum value you would accept for selling all those resources. So in other words, the primal tells you what to produce and the dual tells you what each resource is actually worth. In linear programming and more generally convex optimization, we see strong duality and weak duality show up everywhere. So here's my plan. I'll study from 2 books at the same time. The first textbook, Convex Optimization by Boyd and Vandenberghe. This is a standard reference, rigorous, comprehensive. The second book is The Elements of Statistical Learning by Hastie, Tibshirani, and Friedman. This is where, this is a classic in machine learning. So why both? Well, I want to see theory and application together. Boyd gives me the mathematical foundation, stuff like what makes a problem convex, convergent proofs, duality theory, all that good stuff. Elements of statistical learning shows me where this appears in ML, like ridge regression, lasso, and boosting. Each week I'll share what I learned, maybe a theorem that clicked, a connection I noticed, or something that I'm still working through, or maybe just something I'm interested in. The format will be informal, kind of like this one, working through ideas, explaining on the whiteboard, and showing my thought process. So if you're interested in ML theory from an optimization perspective, or working through something similar, follow along. Okay, so that's week 0. Next week, I'll probably start with convex sets and functions from Boyd and see where that leads. Thanks for watching.